Really? Well, the part that I think is relevant to this particular lesson is the very first notes of this Beethoven's Eroica Symphony. Well, listen to the first two chords, and he builds on that. A magnificent piece of music. The relevance is that we're going to talk today about Einstein's theory of relativity, wherein you'll see that Einstein starts with two notes, two postulates, and he develops a theory which revolutionized physics and is a puzzle to people even to this day. And you'll see why. It's really rather mind-blowing kinds of things. The other thing that's actually coincidentally, he was born on March 14th, which is his birthday then would be tomorrow. And so as luck would have it, the subject comes up. Now, the reason I put it here, where in your text, it's actually chapter 33. The most textbook writers put this in modern physics. But it's modern in the sense that it's really relatively recent. That is 110 years ago. Relatively recent. But on the other hand, it's not quantum theory. See, I would consider quantum theory a major break with physics before its time. This is really not, because what Einstein was doing, as you'll see, he's trying to better understand Maxwell's theory, which is a classical theory. Maxwell's theory came out around 18... Thank you. See, Maxwell's theory came out around 1860. By 1887 or 1890, it had been demonstrated that man could generate the electromagnetic waves that Maxwell had predicted. And as I showed you already, by 1910, they were putting such radio equipment on ships. And a very useful thing, and it was beginning to be a useful idea. But there were still some questions about Maxwell's theory, which were puzzling. And I'll try to explain that today. And it has to do with relative motion and how the laws of physics work in moving frames. Now, relative motion, I have this little joke that I put in here, where some senior citizen, remain nameless, was driving down his usual freeway, his cell phone rings, and his wife calls him up. He says, "Herman, I just heard the news that there's a car going the wrong way on the 280 freeway, which he usually takes. Please be careful." He says, "It's not just one car," Herman says. "It's all of them." So that's relative motion. You see, so Herman is relatively in the wrong way. So Einstein, now what I do here is, I love the way Einstein writes. Supposedly he was a very deep thinker, but he's also very clear and down to earth. So I want to quote to you, this is literally the paper that he wrote, which is now the idea, the germinating idea of special relativity, but it's called On the Electrodynamics of Moving Bodies. So see, he's starting out talking about, it's known that Maxwell's electrodynamics, as usually understood at the present time, when applied to moving bodies, leads to asymmetries which do not appear to be inherent in the phenomena. Take, for example, the reciprocal electrodynamic action of a magnet and a conductor. That's something we've done in class here, actually, and you'll see why. The observable phenomenon depends, you would think, only on the relative motion of the conductor and the magnet, whereas the customary view draws a sharp distinction between the two cases in which either the one or the other of these bodies is in motion. Now, what is he talking about? This is the experiment that I demonstrated to you. It's the question of, I have a magnet and a conductor. I have the spool of wire. Now, Einstein is saying, does it really matter whether I move the magnet with respect to the coil or if I move the coil with respect to the magnet? Shouldn't matter. It's the relative motion that counts. But, he says, and you'll see, we, even to this day, even though Einstein complained about it in 1905, we treat those two actions by two different theories. Let me show you. You'll recognize this. Here's a case where suppose I have, for example, here, a magnetic field. I can't tell, is that? It looks like the arrows are going inward. Okay, so that's downward into the page. And we have the two different approaches, namely, pull the coil this way. Okay? Now, we taught you how to analyze that. We say this is an example. One way of looking at it is look at this as a bunch of conductors, and they have a velocity this way. So you have a Lorentz force, a V cross B, which will produce an electric field this way. I don't know if we actually talked about this. This is called motional EMF, but you can appreciate that this very readily, I'm sure. In other words, what we're saying, we have this magnetic field over here going into the blackboard. I have a loop here, and I have these negative, I have my charges here. Now, if I give this a velocity, I pull the coil out of the field. This is a velocity. I have a B field, so I have a force, V cross B, Q, V cross B, on these charges, and the force will be in the direction this way. So I will move positive charge up here, negative charge here, and I actually create an electric field across this wire by this motion. And what I'm invoking here is Lorentz force. That's on the left side. Now on the right side, we also taught you, if I have this and I have the loop like this, if I pull the magnetic field now, pull the magnet, leave the coil thick, so the wires have no velocity. So we analyze that a different way. We say here, there's a changing flux in this loop, and we use Faraday's law to say there's an electric field generated, d flux dt. We say that by moving this by moving the magnetic field, we're creating an electric field around here. In the field, in the space. Here, we don't say there's an electric field in the space. Here we say there's a force moving the charges, and that creates an electric field. So we have two different approaches to this day, because it's easier to teach this way. To teach it the way Einstein finally explained it is rather harder. So we keep doing it the old-fashioned way, the way he was taught, and he didn't like it. By the way, in 1905, he was 24 years old. Not much older than you and a lot younger than I. So he was a pretty precocious kid, to say the least. So he didn't like this. He said it shouldn't make any... Why do you treat the same process? Namely, you have a a field moving with respect to a coil. One case, you drag in Lorentz force and say that creates a field in the wire because you're moving charge. In the other case, you're changing the flux, and that's producing electric field in the space. And it turns out that the answers are the same. You get the same answer when you're finally through, but you've got two different concepts here. And he didn't like that. So he says examples like this. By the way, this is electrodynamics because things are moving. The wires are moving with respect to the field. The field is moving with respect to the wire. So it's a dynamic effect. It isn't as though everything is stationary. We had electrostatics earlier, but now that's the fancy name, electrodynamics. So he says examples like of this sort, together with unsuccessful attempts to discover any motion of the Earth relative to the light medium, quotes, suggests that the phenomenon of electrodynamics as well as of mechanics possess no properties corresponding to the idea of absolute rest. Absolute rest. Because if these two things, it shouldn't, you don't know which one is at rest. The fact that these two give you the same answer, and also an experiment that I'm going to describe in a moment, said that there is no thing that we can find in the universe. We can say this is at rest, this is not moving, and we are moving with respect to it, so that there is an absolute standard of zero speed. He's claiming that the speeds are always relative to something else, and science will never show that there is something which is a privileged frame of reference or privileged space, which is, you can say, is at rest absolutely. So, I will say a couple of words about in ordinary mechanics, there are no privileged frames of reference, and he's claiming that the same laws of electrodynamics and optics will be valid for all frames of reference for which the equations of mechanics hold good. So these are the two postulates, bum. The first one is that if there's a frame of reference in which mechanics, it says the laws of mechanics work equally well in these frames of reference, the laws of electrodynamics should work equally well. That is, you can't tell the difference. You can't distinguish the mechanical frames of reference from by electrical means. I'll explain that a little bit further. So that's called the principle of, we'll call this conjecture, the principle of relativity, and we'll raise it to the status of a postulate. Another postulate, he says, which is only apparently irreconcilable with the former, namely that light is always propagated in empty space with a definite velocity c, which is independent of the state of motion of the emitting body. In fact, it's even independent of the observing body. In other words, the speed of light in a vacuum will always be the same no matter how it's generated or how you are moving, which is a pretty shocking thing, as we'll see. And that means that the idea that was in the minds of physicists in those years was that there was a medium called the ether, luminiferous ether, will prove to be superfluous, which is really something to say to something, that some concept you believed all your life is superfluous. You're just wrong. Inasmuch as the view here to be developed will not require an absolutely stationary space provided with special properties. So you don't need this medium which has special properties, meaning it's at rest when everything else moves with respect to it. So I love this other Einstein quote. He says that intellectuals solve problems, but geniuses prevent them. So, of course, all the intellectuals at the time were trying to understand this, how light was propagating in the ether. And there were theories and complicated things. And he said, well, folks, it just isn't there. And here's another point. Well, let me give you a little bit of the background. Now, first of all, let me point out that this is a complicated theory, has a lot of parts to it, and it doesn't apply a lot to our daily lives. It's not like mechanics or electricity, ordinary electricity and magnetism, so I'm not going to go into great detail, but I want you to get a flavor of it just to see how a great mind worked, and to give you some feeling for why this is strange. So I have to go back to set the background of the other relativity. He speaks of the mechanics. There's a relativity principle there. And this actually goes back to my first hero, Galileo. This copies a translation of Galileo's dialogue on two principal systems of the world. It was written about 1600, probably. Well, Galileo, look, the point was this. Galileo believed that the Earth was moving around the sun, and people objected to that because they said, look, if the Earth is moving around the sun, why aren't we just being blown away? You know, if you ride on a horse in a cart, you know, the cart's going and people should be going. And in fact, we'd have to be going very fast. I forget the number, but it's interesting to know how fast we are moving. I think I looked this up, or you can easily calculate it. Going around the sun in 1 year, 365 days, going around a circle of 93 million miles, you're going about 35,000 kilometers a second, something like that. It's incredibly fast. So where is this wind? Why aren't we all blown to the back? So Galileo said, whoa, wait, let's think about that. And he says very beautifully, he says, shut yourself up with some friend, you might as well, in the largest room below decks of some large ship. That sounds fun. And there, oh, this is not such fun, procure gnats, flies, and other such small winged creatures. Galileo, great scientist. Also get a great tub full of water, and within it put certain fishes. Let also a certain bottle be hung up, which drop by drop lets forth its water into another narrow-necked bottle underneath. Then the ship lying still, observe how those winged animals fly with a like velocity towards all parts of the room, how the fishes swim indifferently toward all sides, and how the distilling drops all fall into the bottle placed beneath. Okay. And casting anything toward your friend, you need not throw it more force one way than another, provided the distances be equal. You don't have to throw it any harder one direction than another as long as it's the same distance away. So it doesn't matter which way direction you throw it. Okay. Having observed all those particulars, though no man doubts so long as the vessel stands still, they ought to take place in this manner. Make the ship move with what velocity you please. So long as the motion is uniform and not fluctuating this way or that, you shall not be able to discern the least alteration in all the aforementioned effects, nor can you gather by any of them whether the ship moves or not. In other words, in a moving ship, the bugs will fly around happily, the drops will fall into the bottle, the fish will swim around, they won't all get swept to the back of the tank. Right? We believe that. Well, now, see, he picked a ship because that was the smoothest moving object. A horse cart would not move so smooth. They didn't have smoothness, but a moving ship was pretty good. We would say in an airplane going 500 miles an hour, we have that experience. The stewardess pours the coffee, it goes right in the cup. So he says, as long as you're inside, you can't tell whether you're moving. So the relativity means that any inertial frame, any smoothly moving uniform frame, whatever you see standing, what you thought was standing still, will still go on. In other words, if you're standing on the earth, moving at a uniform speed, you can't tell you're moving. We can't, when you walk outside in the street, you can't tell that we're moving around the sun at a zillion kilometers per second. You can't tell. So that's the mechanical principle. This is the laws of mechanics. And what Einstein says is not only can't you tell by looking at how the flies are flying whether you're moving or not, you couldn't even do that with light. Now the point here is, could you, for example, shine a beam of light inside your chamber and measure the speed of light and see whether it's the same as if you were in a stationary frame of reference, you would measure the speed of light. Suppose you're moving, suppose you're inside the ship and you send a speed of light. If the light is traveling in some medium, if you're running against it, it should come at you faster. Sort of like if you're running at a wave coming in at you, like let's say you go to the beach, the wave is coming in, you run toward it, it's coming to you faster. So you would think that if light is a wave, which you knew at that point, Einstein knows it, Galileo didn't know it, but you would think the speed relative to you would go up. And so you could tell that the light was moving in a particular medium, or you might be able to outrun the light, go faster, and the light might catch you, in which case you could say, oh, the light is moving in a special medium, and that's the medium at rest. And that's what people thought in those years, that there was such a medium, and that you could, if you moved with respect to the medium, the light was moving in that medium, the velocity of light would change, depending on whether you were going toward it or away from it. That's a natural enough thought. And that way, if you measured the velocity of light, you'd be able to tell whether there was such a medium, and that would be the medium at rest. That's the one that's carrying the light. And Einstein said, no. That is not true. And the reason is he didn't want any particular frame of reference to be better than any other. And there was scientific reason for that. And the reason, well, he refers to it obliquely here. In later years, strangely enough, he said, let me go back here. Examples of this sort, together with unsuccessful attempts to show any motion of the Earth relative to this medium. You see, people had done an experiment where they tried to see whether the velocity of light changed, whether you're going with it or against it, but the velocity of light being so enormous, just running or getting on a horse or getting in a car or getting in a boat, you could never expect to see any change in that speed to that accuracy. So what the experiment that was done is the experiment, the best one, or the earliest one that was believed, is the one of Michelson and Morley. And this was done in 1887. So they were quite well aware of Maxwell and everything like this. Well, you know, I really don't have time to describe it in detail, but the idea was simply that what they did was a very interesting idea. He had a beam of light coming in from one direction, and he had a mirror here which was not a totally reflecting mirror. So it let some of the light through and it reflected some of the light. So the light came in, and part of it reflected upward, and part of it passed through. So it split the beam. And then he had another mirror over here, good mirror, perfect reflecting mirror, 100% mirror, and another 100% mirror here. So the light would come, and then it would reflect back down, and again, part of it would pass through, and part would be reflected. So you had one path, which was this one, and this one, and then you had this path here. Let me put a different color. The light that passed straight through would go this way and bounce back. And then they would recombine here, and then both of them would end up going here. And the question was, if there was a medium carrying the light, like sort of a wave on water, it would make a difference if the we knew the Earth was moving at some pretty high speed, but not actually the velocity of the Earth with respect to the velocity of light is really around. It's big on relative, but it's only a factor of 10,000th. So you're dealing with a small effect, and it turns out that the effect he was going to try to see is the square of that. So he was looking for a part in 10 to the 8th. It turns out that most of these effects go as v over c squared, which is sort of like 10 to the minus 8th. So he's looking for a very small effect, namely, if the light was being carried by a medium, and these mirrors are attached to the Earth, so they're being carried this way, and if the ether, this thing that's carrying the medium, is stationary, let's say, it's going to sort of blow by us. It's going to come this way, so it's going to carry the light backwards. So what you'd really have to do to make this thing work, you'd actually have to have a little bit diffuse. You'd have to send the light up at a little bit of an angle, because the so-called ether wind is blowing. You're carrying this way, so the wind is sort of blowing this way. So you'd have a wind going back this way. Also, if you're going against the wind when you're going this way, your speed will be lower. On the other hand, if on the way back, the wind is carrying the light, so the speed is higher. When you go through all that, it turns out that there will be a difference in the time. If you put a pulse in here, there'll be a difference in the time going up here, being blown away, blown sideways, and coming back down, still being blown this way. Compared to going this way and coming back, there'll be a slight difference in time, going as v over c squared. So there'll be a very slight difference in time, and he calculated that if the Earth were moving with respect to this medium, he should see it. And moreover, what he does, he said, well, maybe the wind isn't blowing this way, maybe it's blowing a different way. So he rotated the apparatus, and he did it different times of the year, so that if I'm not going, in springtime I'm going this way, in winter I may be going that way. I try all different ways, make sure that he had the wind blowing. And the result is, I actually have the paper here because it's reprinted in this book. I don't know if you can see it from there, but he said, by my calculation, I should get a swing of the speed. As I rotate this apparatus around, it should go like that. I'm getting this. Virtually nothing. No change. You rotate this around, and it's as though there's no wind. And he just couldn't understand it. He says this violates all the theories that the wise men are putting forth, the intellectual solutions. Along comes Einstein, 1905, and brashly says, well, fellas, it looks like there is no ether, but the speed of light is a constant. Because if the speed of light is a constant and there is no ether, the light comes up, the light comes back, the light goes here, the light goes there. There's no change in speed because there's no ether. You rotate it, nothing will happen because you really not change anything. The light goes up. If this is the same length and this is the same length, you send the light up, you send the light. The only thing that was going to make a change is the fact that the wind was blowing this, and change it was a little different here. But if there is no wind, then this experiment gives you zero result because I just send the light this way and that way, and they come back in step. No change in time. If everybody's going at the speed of light, no matter which direction you're going in. So that gets us to Einstein, who says, I can explain this, but you have to say that the speed of light is a constant, but something else has to change. Let me try to do it, Bill. I think what we're going to do is he says, let's analyze a certain experiment. Bill is going to, he's a good basketball player, he's going to illustrate a certain thing, namely of two frames of reference. There's Bill's frame of reference, wherein when he's dribbling the ball as fast as he can. Could I put that? I don't want to trip. The goal for him is to keep the ball near his foot because he's trying to keep control of the ball. Whereas, from his point of view, in his frame of reference, the ball is going essentially up and down, vertically. On the other hand, from your, as a spectator point of view, the ball is going like this, right? So it's going on a much longer path. So there's your two frames of reference. Okay, Bill, you want to go slow or fast, whatever you... Okay. Yeah, see, his frame of reference is pretty much vertical, but clearly it could not have been right. Okay, so, excellent. Let me try to analyze this experiment. Thanks. I may call on you again to do the passing. The dribble experiment, okay. And its relativistic analogy. It's sort of like Michelson Morley. Very briefly, you won't find this in the books, friends, so, of course, we just dreamed this up. But what Bill does, the player, he just starts here and he bounces the ball. So he starts at 0 and he comes down to 1. And he moves, the ball moves a distance, say, d. This is Bill's frame of reference. And now, this is the audience frame of reference. The same d, but in time, it looks like that. In time, Bill is just going up and down like this. So this might be 0 time, this might be 1, 0 time, and 1. And so let's get the velocities in the different frames of reference. The velocity in Bill's frame of reference is the distance over some time. Let's say we had a clock that Bill was carrying. He could know how long it took, say, the ball to reach the first bounce. On the other hand, in the audience frame of reference, you see the time, the distance is greater. Let me call it, or let me call this one D0. That's Bill's thing. Let me call this one D. So the velocity here is D over a time you would measure in a clock. You folks could have measured it in a clock. Now, obviously, D here, this D. Yeah, okay, a little notational problem. Okay, let's call that sideways distance D is larger, and also the time will be larger. So the distance here is actually okay. It would be that height plus the length of his stride squared. In other words, if he makes one stride like this over that length, the distance here is that. But the times are the same. The time for the ball to hit the ground is the same. By classical reasoning, thinking, the time is the same. So if the time is the same and the distance is larger, the velocity in your frame of reference has got to be greater. This is greater than the velocity in Bill's frame of reference. And in Bill's frame of reference, the velocity is equal to basically this velocity times the cosine of this angle. In other words, in Bill's frame of reference, only one component of the velocity is working. So in the two frames of reference, the velocities are different. In other words, we would measure in this frame of reference this length and a time, and in this frame of reference we would measure a length and the same time. That length being different, the two velocities would be different. Now, we have to compare that to what Einstein would have us believe. And here's where it starts to get weird. He says if you do the same dribble experiment with light, so you start out with a source here and you shine a light pulse, and let's say it reaches some other place in a time t in this frame of reference, which we usually call it S prime for some reason. So the velocity here is equal to the distance in this frame of reference over the time it takes. Now suppose we do this experiment where we take sort of a reflecting mirror and a source, and we dribble the light as we run this frame of reference with respect to this one, so that you have something like this. Okay? And let's consider this first path here, the first one, and we're going also at a length L, which is, okay, some distance here. So now the velocity, this would be in the S frame, we'll call V0 and D0. In this frame of reference, the velocity would be this length, again, d prime, over the time measured in this frame of reference, some time, to do this path. Now, I'm going to make a distinction between the time here, because you see, again, we have the same problem. We have that the d prime here is equal to this height d, 0, plus the length of this travel squared over the time measured. So there's nothing so strange about that. But what Einstein says, though, if you measure the velocity in either frame of reference, regardless of how it's moving, you should always get c. So this one should give me c, and this one should give me c. That's the peculiar thing, that by his second postulate, both, you should not be able to tell a difference whether I'm going sideways or if I'm going straight up and down. The velocity of light is independent of the motion of the frame of reference. So now you've got a problem, because this definitely is larger than this d. So that, Einstein says, well, the only thing we have to work with is the time. Something has to change with the time, how we measure time. In other words, the clock in this frame of reference should read something different from the clock in this frame of reference in order that it should read something longer because this is bigger. In order to get C, this has to be bigger. Well, I won't think, do I have time to derive this? Well, the answer, let me not derive it. The answer will come out that in other words, it will come out that unlike our classical thinking, our non-relativistic thinking that the times would be the same, the clocks would run the same, it's required by this kind of reasoning, if the velocity of light is to be independent of the motion, that the clock that measures this has to read a longer time. And that time comes out, the time is given by a longer time. It's the time that was in the first clock over this v squared over c squared. This is the ubiquitous factor, v squared over c squared, that comes into all of the relativistic, well, most of the relativistic things. And so that time will be longer. So this is known as time dilation. Dilation meaning to expand. Like you have dilated eyes or something when you dilate the eyes to look inside. Dilation means the... And what is dilated? You see, we consider the measurement in, as we say in Bill, let's say in Bill's frame, namely where the clock and the person are measuring the same thing. They're going back up and down, and they're not moving. The clock is not moving. See, in the other motion, in the other activity, you'd have to have clocks at different places to really measure the time. If you measure the time with one clock, namely in Bill could have one clock with him. You guys, if you were measuring this, there'd be a clock when Bill got here, and then in order not to have any time delays of looking at the clock, you'd have to have a clock over here. So you'd have many clocks to measure properly a moving object. So in a moving frame, if the thing is moving with respect to you, you'd have to have many clocks. So we call this one the proper frame of reference. I think that's a poor translation of probably some German word. Eigen, it's characteristic, its own personal frame of reference, namely the clock is right there with you. So this is the proper time. This is the time measured in the proper frame of reference. And compared to it, other clocks would measure longer times. Another consequence of forcing the speed of light to be the same in every frame is that you have, if you had a meter stick here, and it have 2 meter sticks, if one of them is moving, and you measure its length while it's moving, it will appear shorter than the stationary stick. So if I'm carrying a stick, here's the thing. I may not get to you the second time, Bill. Sorry about that. Would have been. So you see, you folks would have a meter stick. I know how far apart you are. Now, in order to measure my length while I'm moving, what you have to do is that everybody has to know his position, and you have to have a clock. And all your clocks have to be synchronized so that you're all at the same time. And then all of you have clocks, and we know where you are. As I go by, the nearest person looks to see, what you do. You say at a certain time, you all synchronize your clock and say at noon, say, when the hand is like this, we all look, everybody looks at this stick. The person who sees this end at noon, we know where he is. The person that sees this end at noon, we know where he is. So then we would say the length of this moving stick is the distance between those two people. That's how Einstein says you should measure a moving length. Pretty reasonable. But you have to have synchronized clocks so that everybody at noon, everybody looks up and sees where you are. And if you're right next to this end, that's one end, and that's the end. If you do that, it turns out that the length of this rod will end up shorter than the length of this rod. I'm, see,
You're moving in this.
yeah, I'm the moving rod, but in my personal frame, I measure a length. This is my proper length because I can measure this at my ease. You guys have to work at it. See, I can measure this anytime, and I measure the length. So the proper length, that's the very key thing. You have to know. I'll take that from you so your hands are free. You have to know which is the proper length, and then things make sense. The proper length is the length measured in its own frame. Like if I'm carrying this stick, and I can measure its length. But you, all of you, it takes at least two of you to measure that length. But this is the proper length. So in the proper length, the length you would measure. This is the length you would measure. Compared to the proper length, it's shorter by this factor. See, that factor here is less than 1. The square root of 1 minus v squared over c squared is less than 1. Multiplied by the proper length will give you a shorter length. You'll actually measure a shorter distance of that length by that technique. So those are the kooky things that kind of came out of this by forcing the speed of light to be unmeasurably different. It is not different depending on if you force that to be true, then you have to change how you measure time and how you measure length. And that's what Einstein said, and people are still, so the story is, I think I'll have to stop there. It's pointed out that Einstein won the Nobel Prize in 1921, but they didn't give it to him for this, because they still didn't believe it. It's so weird that they said for services to theoretical physics and the photoelectric effect, but they didn't mention relativity. And even to this day, people are still trying to find, because this is this year's issue of Discover magazine, and the lead article is outsmarting Einstein. They're still trying to prove the poor guy wrong. He's been dead for 60 years, and they're still trying to tell him he's wrong. Because it's so much fun to try to knock off the king, you know. So it's really rather hard to understand some of this stuff, but it turns out to be true. And if you go through it even further, it predicts such things as E equals mc squared, and that matter and energy are inconvertible. Oh, and because of his birthday, we have to have a party. Oh yes, please. German cookies, because he was born German, but he didn't like the German school, so he went to Switzerland to study, so we have some Swiss chocolate. Oh yeah, this is all part of the pattern here. This is German. Leibniz was a very great mathematician. German will come up on your way out, grab something, and happy birthday, Albert. These are good, by the way. These are good. You can read more about it in your book. I don't think we're going to go much more because it isn't too relevant to our lives in a lot of ways.